Okay, so let's continue on this chapter 3. I think this is not quite right. I think it used to be somewhere here, probably. So, chapter 3. So this is about ergodic theorems. Yeah, so if you remember last time, just to recall, so given a dynamical system F that is measurable, so we wanted to study the convergence of the time averages. So we were interested in, and if you have an observable, let's just say it is measurable to start with. So we were interested in this sequence, equals 0 and minus 1. So you evaluate this along the orbit or a point here. Okay, this is what we were interested in. We call this a time average. And if you remember, we had this theorem, which is Kingman Theorem, which is so all the theorems that are relating time average and space average, they are generally called ergodic theorems. That's the title of this chapter. So here we are interested in this, and see that studying this quantity is kind of going deeper, like understanding better something about Poincare recurrence, for instance. Like if this function was the indicator function of a set of positive measure, you have a refinement of the Poincare recurrence theorem. So for instance, we have this Kingman theorem that tells you that, this is just a recall, we studied it last time, is that if you have phi n from M to R that is sub-additive. Sub-additive means sub-additive with respect to F, okay, with respect to a dynamical system. So this is phi n plus M is less than phi n plus phi M composed with Fn. So for instance, this here is sub-additive, okay? And the condition was that phi 1 plus, which is the maximum between phi 1 and 0, is integrable with respect to a measure that is given, and that our dynamical system F is, mu is F invariant. So if you have these conditions, you have that this quantity phi n of n converging to a function C, okay, phi n of n, this is general. As you will see, we will apply it to many type of sub-additive functions. So this is called a sub-additive ergodic theorem. This is converging to phi, and phi is F invariant. F invariant meaning phi composed with F equals phi. And not only that, the integral of phi d mu is the integral, is the limit when n goes to infinity. Like this limit exists, okay? That's also part of the limit of d mu. Okay, part of the theorem is that this exists. So the conditions here are that you have a sub-additive, you have an invariant measure. Then you do this, you have this conclusion here. So in the next chapter, probably next week, we will go more and see, that, this, not only it is invariant, but it is constant like almost everywhere. We will see that when we add some more structure to our measure, which is ergodicity. All right. So probably more than half of the lecture, the second half of the lecture will be dedicated in proving this. And if you remember last time, we have seen that Kingman, so applications of Kingman. So we have seen that Kingman implies Birkhoff ergodic theorem. Birkhoff ergodic theorem. We have stated this last time, so I don't need to do it again. Theorem. And this was just, saying that, so let me state it here. So you have 1 over n, the integral of phi composed with fi x, I equals 0, n minus 1 is converging to some function phi tilde, where phi is L1. So this convergence, what was interesting is for mu almost every x. This is important, okay? The fact that this convergence is with respect to this measure. And yeah, as you can see last time, before I start this section, I gave an example where you can have a point where you don't have the convergence, okay? And the proof of this, uses the way we did in the class is last lecture is we use Kingman for this sequence. So you define this as your phi n, and then you check all the properties, okay? Yeah, under the assumption that the first guy is integrable. This function that you put here is integrable. So I must say, so here we are proving Birkhoff using Kingman, but there is, in the literature you can find a direct proof of Birkhoff not using Kingman. And you will see also in the literature some proof of Kingman that use Birkhoff. But here we will do something a bit different. We will prove Kingman here, and the proof of Kingman that we will use here is due to Arthur Avila and Boki. So what we will do is we will prove Kingman independent of Birkhoff, okay? Not using Birkhoff, because in the literature there are many proof of Kingman using Birkhoff, okay? But here we will do it not using, so this is a proof that was given by Avila and Boki. So we will do this proof in the second part of this lecture. As I said last time, this is very important. This is a very important theorem in dynamical system, as for instance it gives the definition of Lyapunov exponents that I will do in a minute. And yeah, and you can say it is also used in the in the Ozolidis theorem. So in many basic results on ergodic theory, they are based on an utilization of this type of theorem. So if you remember also last time, I talked about the set of points where you have this convergence. That set of points might depend on the function. So always in the recall from last lecture that so given phi that is L1, so Birkhoff says that there exists G phi, says that G phi has full measure, and you have convergence everywhere for every n. This guy 1 over n is converging to phi tilde of x for every x in G phi. Okay, and and this so that the integral of phi, the integral of this function is the limit of this integral. All right, and if you remember, we had this remark last time that if you put more structure on your space, like if M is compact metric space, then there exists G with full measure. There is a full measure set that works for all continuous functions, such that for every phi in C0M and every x in G, you have this convergence. Phi composed with Fix is converging to phi tilde of x. Okay, I equals 0 n minus 1. So the idea is just use the fact that this is separable, and you can do it by approximation. So this is where I stopped last time. Let me just. So proof of this is that M compact metric imply that C0M has a countable dense set. Dense subset. Let's call it phi k in n. Okay. So if you pick any for phi, you define, for every k in n, you have gk, full measure set, for which you have the convergence, such that 1 over n sum of phi k Fix is converging to phi k tilde x for all x in gk, I equals 0 n minus 1. And what you do, you define G to be the intersection of gk's. Right? And then use, from any theorem from measure theory that you have that mu of G is 1, like G has full measure. And you pick an arbitrary, so pick for every, so pick phi in C0, so that means that there exists k in n, such that, so if you pick phi and epsilon positive, there exists k epsilon, such that C0 norm phi k epsilon minus phi is less than epsilon. Okay, and you can always write this 1 over n, the sum of I equals to 0 to n minus 1 of phi k, phi composed with Fix. You can think of lim inf of this, okay, because the lim inf always exists. Where x is in G here, and this is always bigger than the lim inf, the sum of phi k epsilon composed with Fix minus epsilon, okay, because every phi k is close to phi by epsilon, and then you use, you're averaging by n, so the epsilon will get out from the sum, and here the lim inf is actually a limit because of what we know here. And similarly, you can see that also the lim sup of 1 over n is less or equals to the lim sub, which is also a limit, okay? Okay, epsilon plus epsilon. And you combine these two to have that the limit exists, okay? So this is just an easy approximation. So let's go to like the application using the application to the existence of Lyapunov exponents. So as I was explaining last time, when we want to study dynamical system, one aim or something that could reduce, like simplify your study, is to have eigenspaces, is to have like a decomposition of your space into invariant spaces, okay? Like if you have a matrix, I want to study the matrix, what I do is I find eigenvalues, I find the eigenvectors, and I know I have linearized my system, like my dynamical system, into these eigenspaces, and in the eigenspace I know exactly what this is doing. So Lyapunov exponent is just a way to generalize the notion of eigenvalues to nonlinear system. Okay, if you have a nonlinear system, you want to see the notion of eigenvalues, so you can get it using this theorem. And the notion of eigenspaces is also given by Oselade's theorem, but that is a theorem that we will not see in this course. So let me go to Lyapunov exponents. So if I finish this part, I will come back to the proof of Kingman, which is very technical. Lyapunov exponents. So let's just like see the simple case of what I'm saying here. Simple case of the simple case of yeah. So the simple case. Let's take this matrix 2, 1, 1. Okay. We all know we can we can do we know that the determinant of A is 1, and we have 2 eigenvalues. You can solve determinant of A minus lambda identity equals 0, and you get eigenvalues lambda 1 and lambda 2, that is lambda 1 minus 1, okay, because the determinant is 1. Let's call this guy lambda. Okay, this is something you can do for any matrix. But we can see this in another way. Like we can see we can obtain these lambdas as limits. Okay, how do we do that? We look at, so if you take V, so we have these eigenvalues. So these guys, they give eigenspaces E lambda and E lambda minus 1 are eigenspaces. So the eigenspaces, so they are orthogonal, yeah. So because this is the determinant is 1 and so on. So so if you pick a vector, let V in R2. So this vector, you can write it as V lambda plus V lambda minus 1. Like you can write it in terms of these 2 eigenspaces, like a decomposition. So now what happened to this vector when you apply A and V? A and V is just lambda to the n V plus V, V lambda plus lambda minus n V lambda minus 1. Okay? So this is just the definition of eigenspace and eigenvalue associated. So you can see this, I did not say it. So these are inverse of each other. So if one is in 0, 1, the other one is bigger than 1. Let's suppose that lambda is in 0, 1. So lambda minus 1 is bigger than 1. Okay? And I chose this so that there is no eigenvalue 1. Okay? So if you look at log of a n v, this norm here you divide here by n. Where is this going to? This is just going to the bigger one, because this guy will go to 0. Okay, so this guy will dominate. So this is converging to log of lambda minus 1. So one thing I did not say is that this is for like typical vector. Like you have, this is non-zero, okay? This, like say this has modulus 1, this has modulus 1. This is typical. Unless you choose this vector to be in one eigenspace, you will have this convergence, okay? And there will be a constant here, okay? C that depends on V, so because it depends on the norm you have here. Typically, okay? So this is what you get typically, unless you choose this vector to be in the eigenspace. 1 over n log of a minus n v, this guy is converging to also a constant that depends on v, c1, c2, because it just depends on, you know, the norm of this, okay? So this will also converge to lambda minus 1 log of lambda minus 1. So in some sense, what you do basically is you capture this as limit, okay? But in general, you can observe that this quantity here is sub-additive here. This quantity is sub-additive. This guy is sub-additive. So you could say that this limit exists by Kingman Theorem, like the sub-additive ergodic theorem, and also this one. So this is basically what you do for general cocycle. So let's see the general case. So let's say we have let f. So this was just something very simple that you don't need to even do what I'm saying here. You don't even need to use any type of Kingman theorem. So if you have a dynamical system and mu is f invariant, so this is called a cocycle theta that is from M to GLD. So this is a space of matrices. So this is just a way to choose different metrics for different points. Okay, just assign a matrix to a point to a matrix, sorry. So the cocycle defined by theta over f is this guy phi n x, which is theta at fn minus 1x multiplied by theta at fn minus 2x, and then theta at x. So what is that? So you have here this is your space, topological space, and you have a point x here, fx, and so on till fn minus 1x. And on every point you choose, here you choose theta x is a matrix you use, theta x, theta at fx. At every point you choose your matrix. Yeah. So an example for this is, do you know an example of like an example of cocycle? Yeah, I'm saying this type of cocycle.
Yeah. So you have some kind of, when you compose it, it preserves the composition like this.
Mm-hmm.
Yeah.
Yeah. So you can think that if F is a diffeomorphism, you can think theta is like dF.
Oh, okay.
Like the easiest cocycle is that this is a differential. If you have a map from Rn to Rn, you can think of dF as a matrix. Okay? So let me write that. Actually, that's there are many. Actually, some people are doing something. Yeah. Anyway, I think there is a reading course here about cocycles where people they do general cocycles, but the example we will always stay here is just the one for the differential. When the
This is a linear cocycle. You can think of a cocycle like starting from the manifold and entering the space.
yes,
of the
yeah,
manifold.
yeah. For instance, there are this is a simple. Yeah. So this is what I'm saying. Remark is that if F is a diffeomorphism, we can think of theta of x being dfx. Okay, just the differential. Okay, an easy exercise is to check that. Yeah. So if you have this cocycle, you can see that log of phi n plus mx of norm is less than log of the norm of phi nx plus log of the norm of phi m at fnx. Okay, because you have the norm is the norm of A times B. When you have two matrices, is less than the norm of A multiplied by the norm of B. Okay, so this is just to say that this is sub-additive. Log of phi n x is sub-additive. And from Kingman, you can have this theorem which is due to Fustenberg Theorem. So in the book it is so if log of this guy, okay, you have a cocycle. If this is L1, so this was the condition of Kingman, then lambda max of x, which is the limit when n goes to infinity of 1 over n log of phi nx, exists for mu almost every x. Almost every x. So this is just from Kingman, so just application. So the proof is application. Oh, I did not finish the total. So and that this function is also L1 lambda max is in L1 mu, and also you have lambda mean the minimum Lyapunov exponent for 1 over n log of phi n minus 1 of x. This also exists for mu almost every x. And lambda mean is also L1. So this is just an application of Kingman. Yeah, the proof is an application of Kingman. Because we have the sub-additivity, we have integrability, we have mu is f invariant. Sorry, I did not say that. Yeah, so mu is f, yeah. Mu is f invariant, okay? Proof, application of so these two guys are called the biggest and the smallest Lyapunov exponent for the cocycle. Are called the biggest and smallest Lyapunov exponents. For the cocycle theta f. So, and in this example that I say, when you have the cocycle is just given by df, the Lyapunov exponents are called just the Lyapunov exponent of the dynamical system, okay? So, remark. Theta of x being dfx, we say this lambda mean, max, and lambda mean are the Lyapunov exponents. Of the dynamical system. But see that this is just a way to find the smallest and the biggest, but there is also a way to find the intermediate Lyapunov exponents if they exist. And Lyapunov exponent is very important in dynamical system because it's a way to see, like for instance, some people they define hyperbolicity as, you know, a system that doesn't have zero Lyapunov exponents. The Lyapunov exponents, so see that since we have here a log in the definition, so if you have a zero Lyapunov exponents here, that means that you don't see any expansion in your system. Okay, you don't have like the derivative. You think that the derivative is not bigger than 1. It's not exponential. The derivative is not exponential. Like when this guy is 0, and when this guy is 0, like this says that the derivative is not like exponential, like with positive exponents. Yeah. And if you have 0, if you have positive, so if this guy is positive, you can be sure that you have some expansion. So some people, they define hyperbolicity or non-uniform hyperbolicity as just having non-zero Lyapunov exponents. So it's a way to decompose your system, which is also, some people also they define it as being chaotic, like non-zero Lyapunov exponents. So there is a big field of study of these Lyapunov exponents. And also there are a lot of interesting studies about their dependence on the measure, how they depend on the measure. Okay, like if you change the measure, there are many studies by, for instance, by Marcelo Viana. He has an Arthur Avril also. They have a lot of study about the dependence on the measure. So just to tell you that it's a big field of study that exists in the literature. So now, the rest of our time, we will go to the proof of Kingman, which is technical. So, yeah. So the rest is just to do. I will use a new, because everything I have been saying last lecture and today's lecture is based on Kingman. So at least it's good to see the proof to make sure we are not standing on the empty set. So, proof of Kingman. So this is a section. So Kingman is just to use sub-additivity and invariance to have the convergence. Okay, so recall that. So this was Kingman. So Vn sub-additive and mu f invariant. This guy implies that 1 over n, Vn over n is converging mu almost everywhere to some function. So building up to this proof, there are a lot of steps. Again, this proof of Kingman in the literature, you might find the proof in some books using the book of Ergódica theorem. But here, we will do a different proof that is due to Avila and Bocchi. And so, first of all, it makes sense at least to, we want to prove a convergence almost everywhere. So we can get it if we have some type of pointwise convergence and some monotonicity. So for that, let's at least define, so let's prove this lemma. For real numbers, this is a convergence for functions. Let's do the type of convergence for real numbers. So if an is sub-additive, then the limit when n goes to infinity of an over n, this guy exists, and this is the in, and this is on minus infinity. Okay. It's not yet proving this, because this is a convergence of functions. So we will do the same type of for numbers. So this is a sequence of real numbers. Okay, this is on Rn. Sorry. So the way we do this proof is we just define, so to prove this, okay, this doesn't use any measure theory, nothing. So to prove this, let's write L as the lim inf, or the infimum. Sorry. Okay. Okay, and now we, if you pick a number, another number that is bigger than these guys, Yeah, we have to suppose that these guys are not real numbers, because otherwise you will have the infimum to be minus infinity, okay? We suppose that these are real numbers, okay? All of these guys are real. Otherwise, it's trivial. So let B bigger than L arbitrary. So at least we will have that exists K n such that AK over N, AK over K is less than B. Okay, because this is the infimum, so you will have a guy. So if you pick an N for N in N, let's say N bigger than K, you can write N, you can do the Euclidean division, K by N, N by K. So you will have P, K plus Q, where here P is an integer, Q is also an integer, but that is less than K, okay? K minus 1. This is the Euclidean division. And you use now the sub-additivity. If you write a n is less or equal to P a K plus a Q. This is sub-additivity of a n. Okay, and if I want, I divide by n, divide by n, divide by n. Here you can use the fact that AK is less than KB, okay? AK is less than KB, so this is less than PK over N, B plus AQ over N. And see that with this division here, this ratio is going to 1, okay? Because this guy is bounded, K is fixed, so this ratio is going to 1 when n goes to infinity. So what you would have is L is less or equal to, and this is also bounded because the Q, these guys, they belong to a finite set of Q is in between 1 and K minus 1. So that is fixed. So K is fixed. So this is a fixed bounded, is bounded by something. So when n goes to infinity, K doesn't move, so this goes to 0 and this guy goes to 1. So you will have B is less than L. Sorry, what did I say? I'm saying the limb soup here. Yeah. Let's say here limb soup. And here you use the fact that B is arbitrary to conclude that B is exactly, this limit exists, okay? And use that B is arbitrary. Okay. Yeah, so this doesn't use any, just the Euclidean division. Okay, doesn't use any dynamical system. It's just general from real numbers being sub-additive. So how are we going to use this? We define a n to be the integral of this one. So a n to be phi n d mu. So phi n being sub-additive implies that a n is sub-additive. So a n is sub-additive. So by what we have here, so by the previous lemma we have L that is defined as the limit when n goes to infinity of a n over n. Okay. And we also define two functions, phi minus x, to be the lim inf. So the lim inf exists and is measurable. This is of 1 over n, phi n x over n, and also phi plus x. Equal the lim sup so as you can see, the proof consists of proving that these two are the same and their integral is exactly L. Okay, so that's what we are going to do. We haven't seen yet the use of invariance, so that's something we have to track. Where invariance is needed and where sub-additivity is needed. Sub-additivity is already needed here, okay, to define these guys, okay. So there is a key lemma here. But before I write the lemma, yeah. So there are some sets that we define. I will write it and tell you what is the intuition behind this definition. So for k in n, let's define ek to be the set of x in M such that phi j x is less than j. Okay, I actually like to write it like this: phi j of x over j is less or equal to phi minus x plus epsilon. So epsilon is chosen arbitrary. Phi j, where is j now? For some j equals 1. For some j here. So what is this doing? So see that really this guy is kind of capturing the points where you have this convergence here, the lim inf, the points where the lim inf is given. Okay, because this, if you see very well, this is the phi n over n, phi j over. What did I do? Sorry guys, I think you should have corrected this. I wrote n twice, right? Yeah, I think I should delete this. Yes. Yeah, sorry. Yeah, this is very technical. I always try to give an intuition, but I'm still not satisfied with also the direct proof of Birkhoff-Ergódica theorem is also very technical that I think I was never been able to to close the book and do it myself. I must confess, I always need to check something again. Yeah. This is technical, but every part is there is something behind every part. So the definition of this is kind of capturing, because the definition of lim inf is that for every there exists one for such that this is close to this one. And this, if you see very well, it is saying that this guy is close to this one. Okay, in some sense. And see that by definition ek is in ek plus 1, and they cover the whole space. Yeah, so from that From that we define this function. Now this is, this function is defined in a way that the limit now is phi minus, or phi minus plus epsilon, phi minus x plus epsilon if x is in ek, and phi 1x if x is in ek complement. So this function is defined so that the limit, this function is not like lim inf, but the limit of this function is going to be phi minus plus epsilon, and epsilon is arbitrary. Okay, so yeah. You can see that this function is non-decreasing because you have phi k is non-decreasing. So this is because phi 1x is always greater than phi minus x plus epsilon. And you have this for x in k complement. Okay? And you will have that this guy is converging to phi minus x plus epsilon for all x in M. The way I understood this function is when you have a lim inf of real numbers. So if you have this, the lim inf of some real numbers, okay, of some real numbers, what does it mean? It means that you can find a subsequent that is converging. This is doing the same thing in a level of functions. This function is doing the same type of job in a level of function. Like when I have lim inf of a sequence of real numbers, there is a subsequent that is converging to that number. So I have phi minus that is defined as a lim inf of function. I'm now going to find a type of subsequent function. So this is the intuition behind this. Okay? Yeah, so yeah, that's something. I cannot say more. And there is this key lemma, which is very important. Because really the main proof consists of proving that the integral of phi minus is bigger than L. That's the more difficult part, and we will achieve it from this key lemma. So for n bigger than k bigger than 1, we have phi n x. Already, if you see this inequality is going toward proving what I just said, like L is less or equal to the limit of phi minus I equals 0 to n minus k minus 1 ck phi I x plus the sum I equals n minus k n minus 1 of the maximum between phi k phi 1 applied to fix. So this is technical, doesn't use any measure, any dynamical system. I mean, it's just technical, a lemma. But if you see the way this inequality is written is toward proving that L, so this is toward proving this, L is less or equal to the integral of phi minus d mu. Why? Because we know this guy is converging to phi minus. Don't care much about this because you divide its bound, it goes to 0. If you divide here by n, and all these terms here, if you see their integral, you use invariance. So it is the integral of the same function. So you will see that this key lemma will prove this, which is one main part of the proof, the most difficult part of the proof. Okay. Now let's try to prove this lemma. Okay, I have half an hour to do a lot of things. So the way to do it is to do a type of a splitting of the orbit. So if you pick x, let x is in M. So if you pick x in M, you can split the orbit of x corresponding whether you are in the E complement or EK, okay? EK complement or EK. So you define numbers like this. So you have a splitting like M0 less or equals to N1. And we say how are these defined? Less or equals to M1 less or equals to N2 less than M2 and so on less than NL. Okay. So NJ are the, what are they defined? So M's are, the M's are defined to be the return to these sets, to the EKs. So this is how it is defined. So let me get some space. Yeah, because we have to finish this proof today. I don't want to come back to this proof anymore, at least for this semester. Okay, so that sequence is defined as follows. You take M0 equals 0. And what is M0 equals 0? So N1 is the first return to, the first return is the first return time, return time of x to EK. Okay, that means that Fn1 of x is in EK. So see that N1 can be M0, can be 0 if the point was already in EK. Okay? And the fact that you are in EK, it defines M2, because being in EK, that means that there exists a J for which this is true. So M2 from this, so you get M2, M1 it says that phi M1 over M1 is less or equal to phi minus plus epsilon. So always for x, okay? Sorry, this is of N1, okay? This is f N1x is less or equal to phi minus of f N1x plus epsilon. Okay, but what happened is that now once we have M1, we define N2 to be the first return after M1. So N2 is the first return. So this was the first return of x, the first return of Fn1x to EK. Okay, I apply N1x, so I might exit at after N1 I might exist because N1 was just defined as the first return. Okay, it might not stay inside. And then this define Fn2 of x is in EK, and you define M3 and so on. So this is how this is defined as Mj is such that phi mj minus nj over mj minus nj is less than at fnjx is less or equals to phi minus fnjx plus epsilon, and nj plus 1 is the first return of fm1 fmj x2. So this is m1. Yeah, sorry, mj to ek. Okay, let's draw a picture for this, just a diagram for this. So you have, this is m0, and 1 can be the same as n0. So this is the time you stay in ek complement, you're outside. And then this will define m1, where the points are is also outside until n2. Along all this, you are in ek complement. And if you are here, you have this type of estimate here. Yeah. So what do we have here? So this is, you have here NL, and this ML, and so on. So if you use sub-additivity, so by sub-additivity, we have that phi. Yeah, this was at, sorry, this was at mj. Yeah, so this is, I know this is like this, yeah. F phi nj minus mj minus 1 at f mj minus 1 at x. J, yes. This guy is less or equal to, because this is the time that you stay outside, okay? These are the time you stay outside, and if you're outside, you know the function c is given by c1. Sub-additivity is used here, phi1 fjx equals mj minus 1 to nj minus 1. And this is, okay, by definition, this is, because I'm outside for these iterates, so this is phi k at fjx, by definition of this phi k function. And here what you do now is you, and also you see that, yeah, so this is in this part. So in this part also we have to know the estimate we use here. Here we should use the fact that you have this, phi minus, but phi minus is constant along an orbit, okay, because of the definition. You can see that since phi minus, so this estimate is treating these steps. To know the gap, we use phi minus. To know the estimate in the gap is constant along orbit. Then we have phi mj minus nj at f njx. This type of estimate is when you are on ek, is less or equal to. So first you use sub-additivity and you do this sum from I equals to nj to mj minus 1 of phi minus at fix plus epsilon. and this is again the same. Okay. Okay, I think I spend too much time here. So if you do this, add these two, you write the sum. How to say it? You use sub-additivity of phi n to write phi n is less than r equals 0 to n to the minimum between nl and n minus 1 of phi 1 of phi k at fix plus the sum from I equals to nl to n minus 1 of phi 1 at fix. You just take the sum of these two guys that are dividing the orbit, depending on if you are inside, use this. If you are here, use that. Okay, I see that I need to speed up a little bit. Yeah, and if you use the fact that n minus k is bigger than nl plus 1 is bigger than, so nl plus 1 is bigger than n minus k, you get the lemma. Okay, so let's try to finish this proof, and next lecture we go to something else. So from this lemma, what we have, as I was saying, this was, proving, so lemma is that the integral of phi minus d mu equals L. This L. Because this one is obvious, so prove. This one is obvious, L is bigger than, this is obvious. Okay. Yeah, because this is a lim, this is a lim inf, yeah. This is obvious. Using Fatou's lemma, okay? This uses Fatou's lemma. I think I should do something. I should do it, properly. I should do it properly. It's better. Yes. So first of all, because I'm skipping some step. So let's suppose that these guys, phi n over n, are bounded from below. Meaning that exists k says that phi n over n, k positive, this guy is greater than minus k. Okay, so now use Fatou's lemma, because you have for phi n over n plus k for this function to have is less than the lim inf of the integral of phi n over n d mu, which is L. Now the main part is the other inequality, and it is using the key lemma, as I said here. So from key lemma, what do we have? We have 1 over n, the integral of phi n d mu. This guy is less than, so 1 over n, the sum of phi k composed with fi d mu plus 1 over n, the sum of the max I equals n minus k, n minus 1, the maximum between phi k and phi 1. This is the integral fix d mu. This is the crucial step where you use invariance, okay? Where you use invariance. Because here you use that mu is f invariant, you write this as just the integral of phi d mu. So this is I equals 0 to n minus k minus 1. So all these guys being the same is using invariance. So this is actually it's an equality. So this is n minus k over n times the integral of phi k d mu plus the same thing here. Yes. So here you go the limit when n goes to infinity, n first. When n goes to infinity, what you have here on the left is L. So n goes to infinity, what you have here is L is less than the integral of phi k, because this is going to 1 d mu plus this guy is going to 0 because n this step is k, okay? This is k over n times the same thing, okay? Again, this uses invariance, but not crucially, because the number of term is small with respect to n, okay? The number of term is like k over n, so it goes to 0. So when you take the limit when n goes to infinity, this is what you have, and this is the integral of phi minus d mu plus epsilon. Because phi k was constructed so that it's converged to phi minus plus epsilon. And epsilon was arbitrary, you get. Yeah. Yeah. So epsilon is arbitrary, you get the limit you want. But there were this assumption here bounded below. This can be dropped. We can drop the assumption phi n over n bigger than k by like truncating the sequence. So what does this mean? I define phi k n to be the maximum between phi n and minus k n. Okay? If you do this and then you define also phi minus k to be the maximum between phi minus and minus k, you can apply what I did here to this, and you will have that. So use you can see that phi n k over n is bigger than minus k, has this bounded assumption. So this implies that the integral of phi k minus equals to the lim inf of 1 over n, the integral of phi k n d mu. I was dropping the d mu here. Now here you use now another theorem from measure theory, which is the monotone convergence theorem. Monotone convergence theorem, to have that the integral of phi minus d mu equals to the lim inf with respect to k of the integral of phi k minus. Okay. So We are just about to finish. Yeah, and also you have this. You can go further to write this as, because it is the lim inf in K, and this guy was the lim inf in N of phi Kn. And this guy, these two limits, you can exchange them and you can see that this is exactly L, okay? So this proves this, and to conclude the proof, we just need to to prove this. To conclude the proof of Kingman, we just need to prove phi plus d mu is less or equal to L. Because if you combine this with the other lemma, we have the two phi plus and phi minus. They have the same integral. Okay, so to do this, proof. Sorry, there is an assumption for this lemma that I'm skipping. The assumption is that the infimum of phi nx is bigger than minus infinity, implies if you don't have this assumption, after the same truncation argument will give it. Okay, so to the proof, you define theta n to be this function minus n j equals 0 n minus 1 phi k compose fjk. And you can see that theta n is minus n phi k d mu. What did I do? It's the integral of this. Because f invariance, okay? Again, here this uses f invariance, okay? Because mu is f invariant. This is a minus because of that minus we have here. And if you use sub-additivity, what you get is theta n is less or equals to minus phi k n for every n, okay? Because you know phi k n will be less than this type of thing, which you put a minus to have the other inequality. So what you will have here is theta minus. This is a definition, is the lim inf of theta n over n. This guy is less than minus the lim sup of phi k n over n. This is a step that requires a proof, but I will just explain how it works, which is the lim sup of phi n over n, which is minus k phi plus. So this step, the lim sup of this phi k n over n to be k, this one way is easy, like the fact that the lim sup is less than this guy. By sub-additivity, you have it. The fact that this lim sup is less than k times this lim sup just by sub-additivity, because you can write phi k n is less than the sum of phi n, okay, k times, and you put the lim sup is less than the lim sup of the sum, and you get it. To do the other, the reverse inequality, you just do an Euclidean division, okay? You just do a Euclidean division. So yeah, if you want to check it, it is proved in the book, this equality here by a lemma. Yeah, so now once you have this, you will have that the integral of theta minus is less or equal to the integral of minus k, the integral of phi plus d mu. Okay, and yeah, and you can see that here if you use, yeah, here you need to use the fact that this sequence here is sub-additive again, so theta n is sub-additive. I'm sorry, I'm going a little bit fast because I don't want to come back to this proof next lecture. I just want to finish it now because I'm not sure if I will remember next lecture what we have been doing here. So let me just save myself by finishing it today. Yeah, so it's better we do it today that I remember it. So theta n is sub-additive, and also that theta 1, so theta 1 plus, so theta 1 will be less or equals to minus phi k, equals minus phi k, sorry. Yeah, theta 1 is minus phi k, and this is less than minus inf of phi k. So this would imply that theta 1 plus is in L1 mu. So if you have this, you can use the first part of Kingman, which was, to have phi minus is L, and you will have that. Yeah. So you would have that the integral of phi minus d mu is less or equal to 1 over k, the integral of phi k d mu, phi plus, sorry. Yep. And this is converging to L. Yeah, I'm sorry, this is a little bit very sketchy. But you can check again the details from the book. And yeah, there's this condition. As I said, you can remove it by just doing the same truncation here. You can check it again, the details from the book. And yeah, and this finishes the proof, because you will have now, if you have this lemma here, you have this, you have this, where is that? You have this. So you will have the two integrals are the same, and you have the convergence of the function. And I don't need to come back to this proof anymore for this year at least. Okay, so I will close here for today. And I'm writing some exercises. Probably I'll finish it by today or tomorrow at the latest and send them to you. And next week probably we will go to Ergódica. We will do something more maybe attracting than this. Okay, I stop here for today.